You've been sitting on lab data. That's right, and lab data does not like to be sat on. Absolutely. No, no, no. So you came to this video because you have no clue how to fill out a spreadsheet. Well, that's okay. That's normal, especially my spreadsheets. Okay, so we need to go through, we need to talk about where do the numbers go? How do I do these calculations for the chromium and manganese mixture lab? So happy Halloween, everybody, because that's normally when this lab kind of hits, and that's when you start to see these purples and yellows and oranges that begin to take place in a lab environment. So how on earth do I complete the spreadsheet now that I have the data, now that I've made everything, now that I've diluted everything, now that I've given me or the lab tech a mixture to make a known mix? It's your job to figure out what that was going to be. And after we ran it on a UV, what do I do with the numbers? I mean, there's all these like weird things that I need to do. So how on earth do I do it, Tracy? Well, okay, this video is going to tell you. So just a quick review. Procedure. Now again, depending on the year, we might make some slight changes. So just follow suit. The basics of the lab experiments are going to be there. Number one, well, we used phosphoric acid and we made a big batch so that way we could dilute everything with it because it keeps everything in solution a little bit better with these. Number two, use that as your solvent. Prepare 50 mils of an O3 and an O2. And then step three, well, that was way too strong. So you needed to make a 0.003 and a 0.002. And then number four was like, well, okay, that's still too strong. So now we need to use those to make 50 mils of an 0012 and an 0004 and a mix. That's the same concentration. And then number five says, give me a flask or a laboratory instructor, and we will make our own mix. We're not going to tell you how much we used of each one. And then we gave it back to you. You topped it off with the proper solvent, and you inverted really well, and you mixed, and you ran them. Number six, we diluted that with proper solvent. Number seven, we base stored everything from 420 to 600. Number eight, we scanned our chrome, we scanned our manganese in order to get the lambda maxes. And then finally, on the second sheet, number nine, we ran our chromium standard, the manganese standard, a mix that you made, and a mix that I made on the UV. And now we got to calculate the concentrations of each one. And then we get to, oh, this is where the meat and the juices are going to be for this lab. Calculations. It says the E is really molar absorptivity. Notice ABS divided by C, obtained from Beer's law. Beer's law, what does that mean? Well, if you don't know what Beer's law is, F. I might as well just fail you right now. F, 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 F. Ha, 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 I'm felon. I mean, come on, folks. We've talked about Beer's law, lab after 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 lab. Well, Beer's law is A equals EBC, right? That's what Beer's law was. And A is the absorbance, and E is the molar absorptivity, and B is the path length, and C is the concentration. So these calculations that they're telling you to do here, this capital E is actually a molar absorptivity. Why? Well, okay, look what it's doing. If you solved for E, what would happen here is that you could divide each side by B times C. That cancels those out, and we're left with molar absorptivity on the right-hand side, the way that this is written, and then A over B times C on the bottom. Well, for most of the laboratory work that we do in a regular lab, B is 1. And that's because that's the path length of the cuvette. We've not used anything any different. It is 1. Most of the time it is 1, and it was 1 for this lab experiment as well. So guess what? We get rid of it. Look at there. That's all you got to do. So that means that molar absorptivity should be the absorbance divided by C, which is the concentration. And that's what we're doing in the first part of this lab. We're just calculating molar absorptivity. So with E sub 1, we are calculating the molar absorptivity of chromium at the low, what we classified as low wavelength, right? And then molar absorptivity 2, we are calculating the molar absorptivity of chromium at the higher wavelength that we selected. And then E3 and E4 are the same, except these are for manganese. So this is the molar absorptivity of manganese at the lower wavelength value, and then the molar absorptivity of manganese at the higher wavelength value. Keep in mind, molar absorptivity really has everything to do with absorbances, where these things are absorbing light energy, how are they absorbing, and how much are they absorbing, right? That's what this is all about. So in the old way of doing these calculations in the lab, instead of using the matrix, they made you break this calculation down step by step by step by step. And in this first part, it was all molar absorptivity based. That's what these numbers are. That's what they always have been, and that's what they are here. Now notice it says use the exact concentrations that you made in the lab. Now we know that you probably didn't get 0.0012 and you didn't get 0.0004 you didn't do that either. So these are going to be based on the amounts of stuff that you have used in the lab when you made these solutions. So it's not going to be nice and even numbers. And we're going to see that when we do our spreadsheet that we're getting ready to discuss. All right. Next up, they make you calculate a K value, and this K value ends up starting what we call the matrix. And the matrix, I think, is actually easier. I think that it organizes everything where it needs to be. I also think that using the matrix template, just a little bit of algebra, that's all that you need here. It's not very difficult, but it's just going to be a little bit of algebra, some multiplication and division. That's it. I think that actually makes a little better sense than these individual M1, M2s, Ks, blah, 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 blah. All right. So this is what the data sheet has presented to you, because it is another way to do it, and it eliminates the need of the matrix setup, because again, people just feel really weird with the matrix. But I promise you it's not. All right, so here's the spreadsheet. This is what this current year template looks like, and we're going to walk through each individual piece of the spreadsheet just so you know where these values are coming from. All right. So we're going to start with preparation of solution number 1. And solution 1 was your original chromium and your original manganese solutions, right? Those were deep purple. They were super strong. They were not appropriate for a UV by no means. So the reason that we did this, though, is because, like all the other labs, it allowed you to weigh out a comfortable amount, and that amount was documented, written down, and transferred into a volumetric so you can make a solution with them. We do not want you to weigh out 0.0000 something grams. It's just not going to work. All right, so let's talk about this very first piece here under the manganese. So this is just a little bit of review, really, is all that this is, as far as the preparation of solution number 1 under the manganese. So we took 0.1599 in the spreadsheet, and these are the grams that we have weighed out of the manganese compound. All right. So 0.1599 grams, we can't do anything with gram. We need to get to molarity, because that's what this actually says over here, right? Molarity of the concentration. The target was 0.02. So did I get something close? I hope that I did when I do this calculation. So we'll see. So how do we calculate that? Well, the 0.1599 grams of the manganese, you're going to have to divide that by the formula weight of KMnO4. And that formula weight is given. And that KMNO4 is right over here, 158.03. Your spreadsheet template will already have that value in there. And if it does not have that value, then go ahead and key it in. It's a very easy number to get a hold of. So 158.03 grams. So once we do that, we're going to end up getting moles. Now, that number of moles was dissolved in a volumetric flask. And I know that I can get molarity if I have moles, amount of stuff, divided by liter. Well, we didn't make a liter. You didn't go for a liter volumetric flask. You went for a 50 milliliter volumetric flask. So once I get the moles, chunk, that is now taken care of, right? So there's one piece of the puzzle that I need in order to calculate the concentration with. Next up is the liter number. So in order to do liter, I'm going to take milliliters, and milli means 1,000. So I'm going to divide this by 1,000 in order to get liter. Again, something that we've done over and over and over. All of the volumes and the prefix conversions, that's what this is all about. So in this particular case, well, all right, I clicked the wrong eraser, sorry. So we took 50 milliliters, and 50 milliliters divided by 1,000 will give me the liter amount. And guess what? Ta-da! I've got that liter. So when I calculate the molarity of KMNO4, this value comes from the molarity equation, of course. The amount that you actually weighed out, converted into moles, because that's the common language, divided by the volume that you used to make that solution with, and in this particular case, it was 50 mils. Yours might be the same, yours might be different. You might not have 0.1599 grams. You might have something different. You correct for those calculations that you actually did and calculate a concentration. Either way, that concentration hopefully will be really close to 0.02. So if I go back up to the first page, look at this. It says number 2, using your solvent, prepare 50 milliliters of 0.02 KMNO4. And it just so happens to be, okay, this person got really close. First step done. Guess what, folks? It's then rinse and repeat. That's all that this is. So what this means is that we do the same over here for the chromium. So instead of 0.1599 grams, we weighed out something different. And in this case, it was 4420 grams. I still divide by the formula weight, but this time I'm going to divide by the formula weight of K2CR207. 294.18 is that formula weight if you need it. And that will give me moles, and then moles will go into the top of the molarity equation. And then it looks like I also dissolved that in 50 mils because that's what the directions told me to do, make 50 mils of the following. So 50 mils divided by 1,000 is liter, and liter is goes into liter number into the equation. So I take the moles, I divide it by liters, just as I did before, and then I get a concentration for the chromium compound that we have prepared. Again, that should be close to 0.03, and if you go to the data sheet, right up here at the top, number 2, using the solvent, prepare 0.03 molarity of your chromium. All right, so first part done. Just a simple molarity equation. That's all that is. And that will walk you through the preparation. So those solutions are way too strong. The molarities are way too high. So in the next step, it says, using the same solvent, dilute those solutions, number 2, to make 50 mils of the following. So this is where you had to come over to the side and you had to be like, well, okay, so CV equals CV. And it looks like I am starting my initial concentration of 0.02 if I want to do the manganese first. I want to know how much volume should I be using of that strong concentration. I need to dilute down to a 0.002, and the directions say in this particular year, make 50 milliliters of that solution. So there is a straight up dilution calculation is what this is all about. So in order to solve for this, I'm going to use a calculator and I'll bring it up. I don't have a problem with that, right? You can see that on the screen, no big deal. So we're going to solve for the right-hand side of that equation first. So 0.002, and we're going to multiply by 50. That gives me a number. That's 0.02 times x, so we do the opposite of, so that's divide by 0.02, and that will give me a 5. So it looks like what should have happened here is that I should have taken 5 milliliters of the chromium, or sorry, the manganese, 5 milliliters of the manganese, and diluted to a total volume of 50. All right, so in the spreadsheet, it's going to ask you that under part B. So here is the original molarity concentration. Now, your Excel spreadsheet template will probably already be populated to copy a number from up above. And that number is coming from the concentration that is up here in part A. So notice part A says 0.02024, and that's automatically going to get copied here under the original M molarity for your manganese, 0.02024. In order to get Excel, if it's not there, to reference that, you just simply hit equal, and I'll do it. I'll override it. It's not a big deal. I'm just going to hit equal into that spot, and then I'm going to come up here and I'm going to click on the number that I want it to reference, and then I hit enter. So that is how you get Excel to reference another cell based on a value that might be present. All right. Now, the reason that we do this is because let's say I made a mistake, and let's like, oh no, I used 0.1596, not 1599. No big deal. You go in and you put 0.1596, and then when you key that in, it corrects for the molarity of the original solution. And because you just referenced that cell, it also corrects it under part B at the same time. So there's less that you have to do with the spreadsheet if you reference these cells the way that they are. All right. Okay, so in the table that is beside of part B, you are going to see a milliliter, and it says 5, dilute to 50 mils in total, and the solution to concentration is now updated to be a 0.00202. All right. So again, this is coming from your calculation that you made. It might not be a 5 to 50. You might have done something different. If so, those are the values that's going to go in. So 5 milliliters of the strong stuff was pipetted into a 50 ml flask in this scenario. And this is simply a CV equals CV equation again. This is the original concentration. There's my C. This is the volume of that. There is my V. This is the volume that I prepped. There's my second V over on the right-hand side. And the new molarity that is going to be calculated is my second C, which is over on the right-hand side. Remember, CV equals CV. The same thing happens to your chromium as well. So again, if we use this solution that I have prepped up here, how can we make a solution that is 0.003? And the lab direction said you want 50 mils of it. So here is the CV equals CV. So here's my concentration that I've made. Here's the volume that I want to make. And these should be flipped, by the way, but you get the deal. And then here's the concentration that I want to make. How can we do it? You did that calculation. You probably, in this case, the person ended up with 5 to 50. So 5 to 50, solve for dilution. You've got your concentrations. All right. Next up, we're going to go on down because it's actually going to say, oh, whoa, now these are too strong, Nelly. We need to go down to another unit. And once more, we got to bring in dilution equation again. So CV equals CV. So number 4 says using the same solvent, dilute those solutions from number 3, and we need a total of 50 mils, and these are the concentrations that we need. All right, so up here, it looks like you probably did some calculations, or this person did at least, and they're like, okay, well, let's look at our manganese. Made a 0.002 from up above, and I want to know how much volume should I use in order to make this particular concentration of 0.0004, and then finally the total volume is going to be 50 here. So you do this calculation, you solve for the volume just like all up above, and that will give you a target volume that you actually need to use and to make your stuff with. All right, so the issue here is that you just need to keep track of your concentrations, and it looks like based on these calculations, a 20 to 50 would work, and a 10 to 50 would work. So once they use that dilution equation, they're like, oh, okay, so I need 10 mils of the manganese, and I need 20 mils of the chromium. And I can take that to a 50 mil total, and that will give me a target concentration of 0.0004 or 0.0012. So again, you did this prep. You did this already in the lab. You already know what these numbers are. Plug them in. The only difference is that you are using your actual concentrations that you have been solving for into this equation now. So it's not a nice even 0.002. You want to carry that digit on through. So that means reference the cells. Okay, so if I click on the 10 here, you're going to see that is a manually entered number. The 50 is a manually entered number. And then the concentration that's getting calculated based on the dilution equation, it's not manually entered. So what I'm doing is that I'm taking, okay, F17, which is the concentration that has been prepared from up above as we've diluted it. It's not a nice even number. There's decimals, right? It's keeping it all. And then I'm multiplying that by 10 because that's how many mils we used to make this solution with. And then we diluted it to a total of 50. And I take it to the line with phosphoric acid, give it a nice invert and mix, and I hit enter. And here I get a 0.00040. It just so happens to be nice and even showing up on the Excel. But you know, if I go to the home and I start increasing this number, you're seeing it's not a nice even number, right? The same thing's happening with 0.00120. If I increase that, it's not a nice even number. That's up here in the toolbar under number, 0.00 to the left and 0.0 to the right. That's how I get these numbers show up a little different. All right, so this is keeping track of the actual concentrations over a course of time for the spreadsheet purposes of what we actually made in the lab when we did it. All right, so next up says, using the same solvent, dilute the solutions for number 3 to prepare 50 mils of a blah, blah, and then C says a mix that is also the same concentrations. All right, so if I go up here, here is the mix, creating a known mixture. And just like before, these are in separate containers, though. We need to use the same amounts, and we need to take these into the same volumetric flask. It is a mixture of both together. So 10 milliliters of the manganese and 20 milliliters of the chromium were both added into the same flask. So if I take a look at what these values are, here I've got it to reference because these should be the same concentrations, folks. They should be the same thing. But if I take a look, it's the concentration that we made, just like before, times 10. And this should be divided by 50. So I'll reference that cell. Same thing happens here. I take the concentration that we made from up above, 0.03005, times 20, divided by 50, and hit enter. All right. So those are the concentrations. And guys, let's be honest. These concentrations that I'm seeing populate here should also be the same concentrations that populate there. There is no difference between those. I'm going to kind of take this and I'm going to reference this a little bit better. So hold on just a minute. I'm going to shorten these down. There you go. All right. So they should be identical because you use the same amounts in order to make them. The only difference is that these are separate and then this one here is combined. Those are the only two differences between those sets. Same concentrations though. That then sets us up for part D. And part D now is what to do with all the math. What to do with all the UV data. And in that video, we'll discuss it, but that video is going to happen next.